Hi there. So in this video, we're going to look at the second topic about oligopoly, which is game theory. And this is really the study of how the different companies that are the interdependent agents, right? Because they have agency, they can do stuff, how they make their strategic decisions. Now, in a really basic version of game theory, you're only going to have two agents and they're only going to have two choices. In a more advanced game theory class, and you feel free to Google them, there's a great one with MIT open courses. They'll study how you could have more than two, right? And that's pretty cool stuff. It's pretty easy actually to do more than two choices. It's more difficult to do more than two players, but it's really actually just a little bit more excitement in your life. So if you need some more excitement in your life, you've got some game theory that's waiting for you. So let's go ahead and get started with talking about some basics about it. Really what we do in this is we examine the payoffs or the outcomes for various decisions given what the other party is going to do. So like if I know that the other person is going to do blah, then what are the two outcomes for me and which one should I choose? That's all you really have to do. There are some terms that sometimes throw students off. The first is, it's called dominant strategy. And that one just means that it's the decision that would result in a better payoff for you, regardless of what the other agent does. So basically, if you have a dominant strategy, it means that it doesn't matter what the other person's going to do. You should always do that thing, right? And so in the example that I have below, you have maintain tuition and lower tuition are your two choices. And so if one of the two parties, the two schools, JBS or MICDS, if they always will do lower tuition, no matter what the other one does, because it's better for them, then that's called a dominant strategy. So sometimes they'll have them, sometimes they won't. The second term is called Pareto efficiency. And this is actually something where it's related to the idea of a PPC, where you have capital and consumer goods. And if you were on a PPC, right, you can't switch to another point on this level without actually giving up some of the others. So you can't go from, say, point A to point B and increase the amount of capital without giving up some consumer. So you can't make someone better off without making someone worse off. And a Pareto efficient outcome is really the kind of considered a similar idea here. It's the best outcome for both agents involved, and it may not necessarily be where they end up even. So even though it might be ideal for them to end up in a certain situation where they both say maintain tuition, they may not end up there. And so that would be the problem if they informally are colluding rather than formally colluding and agreeing to say, oh, this is what's best for both of us. Now, the third thing is called a Nash equilibrium. And this is an outcome in which no participant will gain by changing their strategy so long as the other one stays where they are. And this is kind of like almost like a gravity well. It's like the thing that's pulling them in, and then they get stuck in this equilibrium and they won't deviate from it. That's the way to really think about a Nash equilibrium, that once they get to this state, they won't deviate from it. They won't move out of it, because by doing so, as long as the other party stays where they're at, by doing so, they'd be worse off. And it's named for a fairly famous economist whose book I normally have right here next to me. So give me two shakes of a lamb. Okay, I found it. So it's this guy, although this is Russell Crowe, just so you know, that's Russell Crowe. And there's a famous movie about him called A Beautiful Mind, and the guy's name is John Nash. He was the book, it's called The Life of a Mathematical Genius and an Economics Nobel Laureate. So John Nash, not always the nicest guy, actually, as it turns out, but he's the one who really kind of early on, along with John von Neumann, they formulate a lot of these ideas. And so he's the first to observe a Nash equilibrium. He's like, oh yeah, they might get sucked into this spot where they won't deviate. In the movie, actually, where it talks about him, there's an example of something that's called a Nash equilibrium in the film, but it's not actually a Nash equilibrium. So if you watch the movie, it's a fun movie, it's cool, but it doesn't really explain the economics behind what he does. Anyways, this is not the same as having a dominant strategy. You could have both parties not have a dominant strategy and still end up in a Nash equilibrium. And it also isn't necessarily the best outcome for them. One thing to observe is that in a two-player, two-choice game, you will always have 0, 1, 2, or 4 Nash equilibria. It's possible to have those 4. You cannot have 3 Nash equilibria. Mathematically, it's not possible. So it's possible for them to get stuck in no spot, where they're constantly cycling around. It's possible for them to get stuck in 1. It's possible for them to get stuck in one of 2 places, and they will randomly actually get stuck in those. Or it's possible for them to get stuck in all 4, in which case they just get stuck in one of the 4 where they start. Now, All of the games that we're going to play in this class in terms of solving these problems are what we call non-iterative, which is a fancy way of saying we're only going to play them one time, one shot. If they play them over and over again, there's actually some other things that come into play, and your textbook goes into that. If you know you're going to play the game over and over again, a lot of times you'll actually play differently than if you only play once. And an iterative strategy that's actually the best one is called a tit for tat, which means that whatever you do in this, you should start by basically playing as the good, right? You do what's good for both of you. And if the other player cheats and does what's just good for them instead of what's good for both of you, then you should do in the next round what they did. You should cheat in the next round. And you should continue to play tit for tat to continue to punish the other player for not playing, what's good for both of you until they learn and adopt the tit for tat strategy. And then you both end up in the most efficient, Pareto efficient outcome. Again, that's an iterative game, right? And that's where that happens is over and over again, where you would adopt that strategy. But in a one-shot, non-iterative game, you don't end up worrying about that. You just do what's best for you in this one circumstance. We will look at another one that probably you've heard about called a prisoner's dilemma, which is a non-iterative game, right? If you only have that one shot, you got to do the best thing for you in that circumstance, so they wouldn't play tit for tat. But we'll look at a prisoner's dilemma as well. Now, let's go ahead and actually walk through what this would look like with a matrix. So you have two schools, two players, John Burroughs and Mary Institute Country Day, two schools, and they both have the same two choices, maintain and lower, maintain and lower. And the way that we read these is by noting that this is revenue, so it's the money coming in, and more money is better, right? So the schools would be choosing whatever one gives them more money. And the one that's on the left, right, the player that's on the left gets the left number. So 26 goes with Burroughs, 54 goes with MICDS. And what these two numbers refer to is this is what happens if John Burroughs decides to maintain and MICDS decides to maintain. And so in that case, Burroughs would get 26, MICDS would get 54. And the way we solve these is pretty straightforward. You pretend like you're one of the two players, and you just assume that the other one will do one of their options, right? So let's start by playing as John Burroughs, and we'll assume that MICDS decides to maintain. So that means we're going to ignore the right-hand column. If MICDS is maintaining, then everything in the right-hand column goes away. And so from John Burroughs' perspective, they could get 26 by maintaining, or they could get 30 by lowering their tuition. So what's John Burroughs going to do if MICDS maintains? Well, they could get 26 or they could get 30. They'll prefer 30. So we're going to circle 30. And now, if we're still playing as John Burroughs, we're going to assume that instead, MICDS decides to lower tuition. So we're going to ignore that column that we just looked at. And so now we say, okay, John Burroughs, because that's who we're playing as, if MICDS lowers tuition and we maintain, we'll get 16. If MICDS lowers and we lower, we'll get 22. So what should we do? Well, we should lower tuition. We would prefer 22 to 16. So let's circle that. And now we notice that no matter what happens, right, if we're John Burroughs, we should always lower. So that means we have a dominant strategy. And so it is to lower tuition. That's what that one means. Now, let's play as MICDS and see what happens. Now, MICDS knows this information. They know that John Burroughs is going to lower. And so now we're going to read it across. We're going to compare this 44 to this 48. So it's switching the directions that we're comparing now because John Burroughs is choosing to lower. And so that leaves us, MICDS now, with the two choices, 44 or 48. Well, which one are we going to do? We're going to choose 48, which is to lower tuition. So we circle that. Now, assume MICDS, we're playing as them, assume that John Burroughs is just dumb and they choose the wrong thing. They choose to maintain. What should we do in that circumstance? Well, if we're MICDS and John Burroughs maintains, we can get 54 or we can get 60. Which one do we want? Well, we want 60. 60 is bigger. So we also have a dominant strategy to lower tuition, right? Because we will always lower. And what will they do? Well, we can actually find out if they're both going to always lower, they will end up in this Nash equilibrium. We have two circles in a box. Two circles in a box is a Nash. And that means we're going to be stuck there. So we're going to both lower. And they won't have any incentive to deviate from that even if they're better off by doing something else. And in fact, you can see if they both maintained, they'd be both better off, but they won't do that. They won't. Now let's do this last one here. AC/DC taxi and Clifford taxi. And this is from the Jacob Clifford problem, but I feel like we could just do it here together. So let's play as Clifford taxi first. AC/DC taxi will assume that they maintain. So we're going to ignore the right-hand column. Right? When AC/DC maintains, we're just going to look at this one column. Clifford taxi can maintain and get 140, or they can lower and get 130. And so they will maintain and get 140. Now what happens if AC/DC lowers? What should we do? Well, Clifford can maintain and get 120 or lower and get 150. Well, we'll choose 150. And so now we can see that Clifford doesn't have a dominant strategy different from that Burroughs problem. But now let's assume that we're planning as AC/DC. Let's assume that Clifford decides to maintain. And if we're AC/DC, then we can maintain and get 150, or we can lower and get 110. Well, what are we going to choose? We're going to choose the 150. Put a circle there. Now what happens if Clifford decides to lower? We can maintain and get 120, or we can lower and get 100. So we should maintain. So AC/DC will always maintain its price, but Clifford taxi doesn't have a dominant strategy. So we know the Nash, 2 circles in a box, is maintain, maintain. What will they do? They'll do that, right? They'll both maintain. And then the last part of this problem is redraw the payoff matrix showing a subsidy of 20 to firms that lower prices. Maintain, lower, Clifford, AC/DC. So if they maintain, then they both stay the same, 140, 150. Now if they lower, then they get the extra 20. So this number is going to get 20 added to it, this 130. But this number should stay the same because it's AC/DC maintaining. For both of these two, we're going to add the $20 because they're both lowering. 120. And then for this one, the first number is going to stay the same because this is an example of Clifford maintaining. So this is still going to be 120. This 110 is going to have 20 added to it for 130. And in fact, we can resolve this problem actually, and we'll go ahead and do that here. Fairly quickly. We can see that now, right, if AC/DC maintains, Clifford will lower because they get 150. If AC/DC lowers, then Clifford will lower because they get 170. So we're comparing 120 and 170 and 140 and 150. On the other hand, if you're AC/DC, you can get 150 or 130, so you get 150, or you could do 120 or 120, and you're ambivalent about that point. So we can actually circle both of those. And we could say here, then that they'll end up either here or here. Either one of those two would be fine. So hopefully this helped you with game theory. I'll see you next time.